other students would also be excited about it. So we went from there into, well, how can we, simplify it a little bit so that it's something that anybody can do. They don't need to be seniors in college. So I'll start sharing. There we go. All right, so go over a little bit of an overview of the program. Basically, what I wanted to go over today is we have about 2 hours. Take a break partway through, probably. What the program is, a little bit of how we put them together. I'm going to go run downstairs and grab a bot and bring it up during our break for us to take a look at. Talk a little bit through the coding. As a general overview, my objective with it was we've set up the workshop so that we give you everything to put it together and have it running. Right? If it's a running functional bot, but it's not perfect, and the reason it's not perfect is so it drives the students to want to fix it. And what I mean by fix it is the base robot with the code that will give you the bot goes forward and turns, but it doesn't go in reverse. So if they want to make it go in reverse, they've got to go in and look at the code with us and see, what math did we use to interpret the signal from the transmitter and receiver to drive the motors, and what did we leave off to add to make the reverse functional. Then there's always things in the way of customization that they can do once they get excited about it. But so the goal is really to get them excited enough about it over the course of a couple of sessions that they want to go and do more with it, have their own event there in the local school, come see ours, and compete in ours if they want. All right, so what I mean by the competing, there's a couple of different weight classes. The two that I've decided to focus the events here at Tech on are beetle weight, which is what our seniors build. They're 3-pound robots. I'll have video of that here in a minute. And the ant weight is a little closer to what I envision doing with middle and high school students for a couple of reasons. One, they're cheaper, easier to build. Well, really, that's the reason. They're cheaper and easier to build. They don't take as much time as goes into the larger, heavier robots. The rules are a little bit more complicated than simple weight. The 3-pound or the 150 grams is based on if it's a wheel-driven robot. If they decide to make something really inventive, like it has legs and walks, they get weight bonus. They can make it twice as heavy. Or if they've got something where instead of wheels, it has camshafts that kind of sort of step like an inch bug kind of thing, they get half of the weight bonus. So they get 4.5 pounds instead of 3. All right, so like I said, here's some videos I'll play here briefly. These are ones that our students made from last year.
Ice cream sandwich, I like that.
Yeah, and please, you guys have questions, chime in. I think there's only 7 or 8 of you in this session. I'm happy to talk through and answer anything. Yeah, so ice cream sandwich is one that the students built. We had 3 bots in the competition last year, 2 that our students built and 1 that I built. The matches are 3 minutes in length. You could win either by knocking out the other bot, or you see at the table there, there's a couple of judges. If nobody's knocked out at the end of 3 minutes, there's a scoring system.
Goomba, I get it. It's pretty funny.
Thanks. And so Doombot is mine. So for April, we tested out the arena that the seniors built, and had a couple of our own bots to do. We still weren't open to the public due to the pandemic, so it's just those.
So how is knocked out defined?
That would be knocked out. It can't move.
Okay.
Or it loses functionality. Like if it's a two-wheel bot and it's only got one wheel working, so all I can do is spin around in a circle. It can't really control itself. That would be knocked out.
And we have a question in the chat asking, will they have access to this presentation?
Yes, I can definitely share this whole thing with you all. Thank you for pointing out the chat question.
And Dr. O'Malley, I'm hearing some feedback from your audio there. Is there anything you can see there on your end?
Does this help with the feedback?
Might. It's when you talk, there's a little bit. It's not a big deal, but was present there the whole time.
Okay.
When you were talking. That might be better.
This should cut it out because it should just be playing to my
yeah.
Yay, the joys of teaching via Zoom. Yeah. Okay, yeah, and you guys can definitely I can send the link to this presentation. The videos and things in here are all up on my department's YouTube site, which I'll also put together and have basis in that. Or if you want to ask, actually, just put in the chat my email address if you want to contact me at nmt. All right, so that's a little bit of what we can do with it. Like I said, those are the bigger, heavier bots, take more time and resources to make. The seniors will make them over the course of one semester. That's not to say that I wouldn't envision a high school or middle school group deciding to do that. It would probably be just more than you would do in a classroom setting. It would probably be an after-school activity if they were to go that far, which would be great. So our objective here is to teach a couple of principles through the course of the workshop, a little bit of engineering design and decision making. The bot I'll give you, like you said, or work the class through building is not optimal. It's a little heavy. We could make some big changes to it. We could certainly swap out batteries to reduce weight, change the frame design. Those would be the two easiest things. They could look to revise the code so the bot could go in reverse. And they could look to add a weapon. The one that we'll build is basically a variation on the Doombot one you saw there, where it's just a wedge to drive around. It's not as exciting. It won the competition because it was simple and straightforward. I broke both of the other bots. They tried to get really fancy with theirs. The students did. Yeah. Yeah, so the one we build isn't specifically, it doesn't really quite fit in the 150 gram. It doesn't really fit in the 3 pound. But it leaves them halfway in between to decide, do I want to add weight to it, add a weapon to make it heavier? Do I want to trim it down a little bit in weight and go to the lower class if we wanted to do the class. If it's within the school, right, then just call it, make it in between weight class. There are in between. Okay. So this is the bot that we started with on the left. The newer variation of it, we 3D printed into pieces and glue them together. It's a little faster. The third iteration that we did this summer with Upward Bound was we made them out of foam cardboard or cardboard for the frame. That way it was a little bit easier to let the kids see they get damaged as they crash into each other and push each other around. The basic parts are essentially an Arduino system. So we've got an Arduino microcontroller, an RC card transmitter receiver, a battery pack, and a motor driver. These are Arduino motors and wheels, so they already work well with that system. Yeah. So, excuse me. I've got this fabrication process here. So we've tried to build it around, my vision was following an IKEA format. We make this bigger. So here we've got the base parts. Yeah, so I see that in the chat, ask about Tinkercad. That'd be great. It would be wonderful if the students wanted to take it. So one of the other things I'll say about my vision for the program here is that it's customizable, right? If you guys have got 3D printers at your school and you want to use those, you've already trained the students. If your students are really good with Arduino and you want to take it a slightly higher level, that's easy to do. If you don't have any experience with that, if the kids in your program haven't done any of it before, we can, like I said, provide the code and just do a couple of things with the code. So approximate costs to build a bot is about $80 to $100. And so what MESA wanted to do, provided we buy enough parts in bulk and that kind of stuff, is I believe what they've said to me is, if we get through this training today, if you want to do it, I'll call in to your classroom for 4 class periods and help work through it. And if you're committed to doing that, then they're going to cover the cost of the startup kit. Obviously, if your kids get really into it and want to design their own parts and 3D print extra stuff, but you know that's extra cost and it's extra stuff. But what is approximate? Yeah, you're in. Okay, great. So yeah, so this is the base kit that we built from, and like I said, it's Arduino wiring. Everything is just the push-in connectors, with the exception of the ace bridge. It has screws on it, so they'll need a little screwdriver that wasn't in the parts list here. But basically, we walk through with some pictures. How do we connect each one of the parts? We have to pull a couple of pins off the H bridge, and basically we talk through them. What that does is that allows the motors to pull 12 volts instead of the voltage of the 9-volt battery or the voltage of the AA batteries. It actually pulls all the batteries together. So we end up with 5 volts going to the the Arduino itself, and then 12 going to the So we did, the way we did it, the last time I taught this, I taught it at UNM Valencia. They organized a thing for me to teach it to high school classes and their students. And so we did it over Zoom. We assembled all the kits here at Tech and mailed them out. And so I buy 300 wires and separate out, everybody gets 16 of them. The little colors are not all the same. So they have to maintain a log of what their wiring diagram looks like, which components go where. That way, if something falls off, some breaks, they can go in and troubleshoot it. So just some more images of putting it together. Transmitter receiver that we use is 3 channels for RC car or boat or something like that. It's relatively plug and play. The big thing that the big implication of that is RC cars are built around, there's a drive, so there's a throttle that controls the speed, and then there's a separate motor that turns the wheels for steering. We didn't have that. We have 2 wheels, and we control the speed, or the speed by controlling the speed of the motors, and the direction by making one wheel go faster or slower. So they actually have to do some algebra in order to take the signal that's telling the steering motor which angle to turn to and use that to decrease the speed of the left wheel to turn left, or increase or decrease the speed of the right wheel to turn right. So figure out which angle we're trying to turn to, and so the code that I'll give you already has that, and that's the part that we need to look through to understand how the algebra is working in order to also implement reverse. So the only thing that needs to be soldered sometimes Amazon will ship the motors without wires attached, and those need to be soldered. Usually we try to find the ones that are soldered already. What I was going to do, work with MESA, is if you guys didn't have soldering tools, techniques, experience, and you need us to do it, we can do that. Right? Because it'll really literally be 4 wires that need to be soldered to each motor. The other end of all the wires are not. That is certainly something that if the students got really into it and wanted to solder their own, it's more robust that way, right? Less likely to fall apart when they crash it around. But the goal here, at least initially, was we'll put it all together. They crash it around, the wires fall off, the wheels fall off, they lose the match, the other team wins. You pack it up and can use it again next year, next semester. Hopefully nothing's destroyed, broken, other than the cardboard frame on the bottom. Yeah, and so the piece of the code that I want to talk about a little later today will be about that the algebra part. So these 2 pieces here, the motor driver is in red on the left, the power supply. It's actually a breadboard power supply. We don't need a breadboard in our application, but it was a convenient way to satisfy some of the other requirements of a Battlebot. Its 2 biggest safety things is it needs a light that lights up when it's powered, and it needs a single button to turn it off. So the breadboard power supply has that. That white button turns it off, and that green light lights up when there's power. So basically, we ran all the power through that to run the system. Again, more things for them to fill out in the instructions. Like I said, this is all on the website, as well as a link to it in the presentation I'll send. Read it line by line here. All right. So when I did it over Zoom with the community college, there were about 50 to 60 students in a bunch of different classrooms around the state. Kind of crazy. It took better part of 2 hours to put the kits together, doing it in their house. For me to put it together with some of my students here that have done it a couple times, probably about 20 minutes. So I'm envisioning a class period as long as we're not doing 60 students in 12 different classrooms at the same time. To put it together and have it running might take a little longer than a class period, but shouldn't be anywhere near the 2 hours it took when a bunch of people opened it up to Zoom at the same time. 2 of us trying to answer questions. So I want to talk through some here about what we're doing with the code. So we've got that RC controller, like I said, that's built to control an RC car. So it's got direction and it's got throttle. It's got a third button that we could later use to control a weapon, or basically turn the weapon on and off. In an RC car, it turns the lights on and off, generally speaking. So because of that, we need to develop those equations to convert the signal into what we need. And then my students also have in this presentation we got here at the very end, how we make it drive a little smoother. It was really jerky the first time they put it together, and so they kind of had to limit the throttle and some other things. Okay. So some definitions before we get too far into it. We've got PWM, which is essentially pulse width modulation. It's the type of signal that we're getting out of the well, it's the type of signal that the motors want to see. And so we're going to have two types of signals. We're going to have pulse width modulation, and we're going to have PPM. The PPM is what the transmitter and receiver wirelessly transmits from your handheld controller to the robot. The PWM is what the motor needs in order to go. It's also what the joystick uses. So our system here ends up taking, if I have a joystick and I'm using the throttle or the steering, it's taking the PPM, is converting it to, it's taking the PWM, converting it to PPM to transmit it wirelessly. Then the receiver takes that, and the Arduino has to process it back into PWM. So the big difference between them is whether we're modulating the width of the pulse or the frequency. So the PPM, basically we take a whole bunch of data and we compress it and transmit it in a single pulse. This is more like what my Wi-Fi is using and not working on my laptop this morning. Than what the motor is seeing. So interrupt service routine. So it's general terminology for a section of code designed to be executed in response to an input. So so this is a little bit, I wouldn't show this to the students right away. This wouldn't be where I started. I just wanted to essentially define the term because it might come up later. It's not necessary for what we're going to do. So what I wanted to focus on today was this part, talking through what the path of the signal is through the components, and then talking through how my students got around programming it, that algebra piece. Okay, so I've got essentially 5 devices that I transmit my signal through before it gets to the motor. The joystick and the controller, the transmitter, which is also in the controller, then the receiver, which is in the robot. So the joystick, we take that PWM input because you're essentially moving, it's not a motor, but you're moving the sensor through the range of its, through its range is kind of like you're moving the motor and you're showing it where to go. So that's PWM. The transmitter converts that to PPM, the receiver receives it as, and then the onboard microcontroller within this receiver converts it back to PWM because it's expecting to drive that RC car motor. And so this is then where we need to go and take a look at pulling it into the Arduino, fixing the signal, and sending it to the motor. That's essentially what we're doing. So we're going to read that PWM signal coming out of the receiver, reverse it back into microseconds. So we're actually going to send it back to PPM. So actually PWM drives the motor. The receiver in the bot converts the PPM that was over the wireless to PWM, but it converts it for an RC car that we buy at Radio Shack. Obviously, more Radio Shacks, but Walmart. And so since it's converted it to that for an RC car, it's wrong. So we essentially, the first thing we do in the Arduino is we take it back and we undo what the built-in receiver did. Then we recalibrate it to control the type of bot we have and finally turn it back into the PWM. There's an easier way to do this. We could just buy something that will control the kind of robot we have. But then there's no math for the students to do. So that is certain. If they wanted to make this a club activity and build a bot, that'd be certainly a way to reduce weight. If they just bought the piece that did all the math for them and converted it straight into what they wanted, it would be lighter and more efficient and all those things. But there's no learning. That's not fun. Well, maybe it's fun, but it's not what we're here for. So and then the motor driver essentially takes that PPM, and what comes out of the Arduino is only 0 to 5 volts, because that's all the Arduino can handle. The motor really needs much more than that, but I mean, it can go with 5 volts and just go really slow. 12 volts will have it zipping around the floor and crashing into things. So that's why we need the motor driver. The motor driver essentially acts as a gate. It provides 12 volts to the motor, and then the signal from the Arduino essentially, like the gas pedal in your car, it throttles it. It tells it how much of the 12 volts to send based on the 0 to 5 volt scale. So this is just a visual representation of what I've tried to describe here. Maybe we should have gone first with that. We've got the PWM going across through the system, the Arduino converting it back. We do our equations in the code and then send it out to, so this 2.4 gigahertz PPM is what's transmitted wirelessly, and then this microsecond burst part is what the Arduino has converted the PWM from the receiver back into to do the equations. All right, so PWM is a very simple waveform, but somewhat challenging to reverse. reverse. The Arduino is constantly checking all the RC channels, and the thing I didn't really explain, the ISR, that's built-in code that processes those signals, right? So there's a piece of this that they're, to get into that part is probably, we probably have a few students in high school that really want to do it. More than likely, it's the ones that want to go on to be software engineers, that kind of stuff. In college, they'll be the ones that dive into that piece of it. So we're going to take some portions of it that are really complex code, and we're just going to take it from somebody that's been an expert and already written it, and we're going to limit ourselves to using what they've done. And so basically the Arduino constantly checks if there's a change in the pulse that's significant, it went from high to low or low to high, then it's going to trigger it to do the math and recalibrate things and change the steering of the throttle. If it's still within some margin of error with its initial value, it's just going to go with what it's at. Right? So that's part of what we've got in there to help it drive a little more smoothly. All right, so a little bit about why we're taking the time to convert back and forth between the two. It really gets back to using base code that controls motors versus codes that transmit signals. Maybe we'll pause and ask you guys a question here. How much do you care about that part?
I've got a question because I'm teaching middle school students right now. So I have a class. I mean, like, I understand this, but you know, but so I have 7th and 8th graders. Our honors math class for 8th graders is Intro to Algebra.
Okay.
So I think and I have 2 8th graders that actually go to the high school for math that are in my coding class. You know, we've done block coding, we've introduced Arduino, you know, and I have some of my kids in that class are in MESA as well. What level of math would this be if they're in Intro to Algebra? Is it going to be too much for them?
Let's jump to the math piece. So this is the math. I don't think so.
Yeah, they could do that.
Yeah.
Especially if we worked in conjunction. So I work with their algebra teacher as well. So we could have that be part of what they're learning in math as well.
Yeah. Essentially, we're going to define some variables of power and angle. Those will be the two things coming from the controller that you input, right? Power being your throttle speed, angle being what direction you're trying to steer it. And so as the angle changes, right, if there's no angle value, it's just power, it just drives the two motors at the same speed. And so the coding piece of it is this one page back here, looks at the values. If there's no steering thing coming in, it just drives the motor, both motors at the same power, and it just goes forward. The code doesn't like negative values going to the H bridge, so which is why it always goes forward. So that you know when they want to make it go reverse, essentially we have to switch the polarity of the pins. So we flop the current, so it goes the other direction, and that turns the motors to reverse. And we'll do that here just in the steering code. So if the angle is within the dead zone, so it's either at 0 or we set some threshold, it just goes straight. If it's outside of it, either going left or right, so anywhere from -175 to -350 goes left, +175 to 350 goes right. Then we switch to one of these else if, right? So we've got a couple of nested loops here for it to evaluate it, and so we'll have to talk through with the students, you know, what are we doing with the code here making these loops. It's checking these inputs from these two things, angle and power, which come from steering and throttle, and then if it is right, so if we're trying to turn left, we take motor 2 and it just remains at whatever throttle speed we've got, and motor 1 we slow down. So we slow down the left motor, cause it to turn left. And based on how far you've turned the wheel to have it turn left, dictates how far you slow it down. Right, so you get a sharper or more gradual turn out of the motor or out of the system. And then the same thing for the right. And when we have positive values coming out of angle, we have that way.
This would be great too. I think, you know, like since I have like a mixed level class, I can have a group work on the coding, a group work on Tinkercad and doing the 3D printing or the designing or, you know, building obstacle courses. And, you know, we were just looking at XY coordinates, which some of the kids don't know yet, but they could actually just figure it out on their own through experimentation. So I think the kids are really good at, even if the math is maybe a little iffy for them, they'll just change the numbers till they figure out what makes it do what they want, you know?
Right. So there'll only be one angle value. This is like I've got one for steering, right, forward and reverse, not for steering, sorry, for throttle. And then I've got something that does left and right on, this is a far more advanced controller than is needed. It has 16 channels and we only need 3. So I'm not gonna have you buy this. We'll just buy, I'll show it here in a minute. Right, so this one is what generates the angle signal, right? When you move it left, it goes 1, negative, move it right, it goes positive. So it's just one angle signal. Yeah. Okay. So yeah, this is the math behind it. Like I said, it only likes the positive values. So what we do when we get the negative value, we can't send that to the H bridge. Instead, we make, so we've got these polarity pins on the H bridge. So 1 and 2 go to one motor, 3 and 4 go to the second motor, and we program them to be high and low. And essentially the signal that we send to the H bridge is if we want to go in reverse, swap. So when you go and you take it and you say, all right, I want to go right hard, and I push it all the way over to the end. The code sees that, it slows down the right motor, and then once the right motor is going slow enough, it switches the polarity so the right motor goes in reverse, and the bot spins on the dime, or close to it. And so essentially, when I'm driving forward or steering just a little bit left or right, pin 1 and 2 here, IN 1 and 2 are high and low. And that's forward for the motor on the left. Pin 3 and 4 are high and then low. That's forward for the motor on the right. I want to go right really hard. It leaves pin 1 and 2 the same configuration and swaps 3 and 4, 3 becomes low, 4 becomes high. Going to the second order to spin that one first. So hopefully they can look at that and draw the conclusion, like we asked them at the end, how would we make it go in reverse? Why doesn't it go in reverse? So, well, if I have throttle go negative, then I need a new line of code that says, okay, well, when that happens, right now what the code does is take the absolute value, it just converts to positive and runs through everything. I gotta take that away, and if I go negative with the throttle, I gotta reverse everything. I not only have to reverse, like the bot goes backwards, but the steering is all flopped. So I've got to basically repeat all of this algebra code that I've got already, but swap everything.
You're just making the front the back.
Yeah.
Yeah.
Back.
Effectively.
Yeah. So power is not constant. It will, based on how far you push the joystick, make it go faster or slower. The students have built into, they found that it goes too fast if you let it go to full speed. So the bots also currently have the code limits the throttle speed. They could take that off, right? Once they find that line in the code, they can say, well, I can go all the way to 350 with the throttle speed, but you've limited it to 275. Why? And they'll probably find out that they switch it to 350, and in an 8-foot by 8-foot arena, it means the bot smashes into the wall before they have time to steer it. Which is fun, but yeah. All right, so we've got negative. Yeah, I kind of already talked through this. The negative PWM controls that. Well, essentially, what we do is we switch that 3 and 4 high and low. All right, I wasn't sure. I know Drea used to work here and already knows a lot about Arduino, so she doesn't need this. But I stole from my intro to mechanical engineering class. We introduced the students to Arduino and modified our worksheet with the class a little bit. So this is also on the website and in the slideshow. It lists a bunch of websites you can use to zoom in a little bigger. I can't find the. Anybody remember the command for Zoom? To zoom in on the screen. My other computer is touch screen. Oh well. Anyway, the website and forum for the Arduino system, Adafruit and SparkFun make a lot of components for them. I think somebody mentioned Tinkercad. They can work up their schematic and wiring diagram beforehand in Tinkercad. The one I use in classes here is a regular Arduino. The one that we've got right now in the bot is an Arduino Nano, which isn't as well supported in Tinkercad, but it's smaller. It has much less versatility. Not much less. It has a lot fewer pins, but we only need like 10 of them, and the regular Arduino has a lot. What do we need? So this activity here also works through, in a little more detail than what I've put in this presentation. What is PWM versus analog? So essentially, maybe take a minute and look at that on this. So the PWM, right? we've got some pulse width, and that tells it how fast to drive the motor, right? The signal it's sending is how long the pin is on versus off, right? So full throttle would be full duty cycle down there at the bottom, sending signal continuously all the way off, no signal, 25% power, 50, 75. You know, how long we're on versus off coming out of it. So that's the signal the Arduino is sending over to the motor driver. Yeah, and then so we've got a worksheet here for them to do at the end of it to look at that, and then I've got code here that just set up their Arduino to do blinking light, and they have to look through the code and comment on what the numbers are, what they're significant, what the sign will represent. Just like what we talked about with our motor system, polarity. And then describing what the PWM is after the there's an answer key for all of this. Okay. Sorry, excuse me. So during our initial code development, the robots drove pretty poorly, right? They were jerky. When the other problem they had is when driving and steering, it happened so fast that the wheels would fall off. you could literally drive the robot apart because it's if you've ever used the Arduino motors, it's a little plastic shaft that's flat on one side instead of perfectly round, so it's keyed to fit the wheel on it, and it just slides on. You could certainly hot glue it together and you wouldn't have a problem anymore, but then it'd be glued together and you could never take it apart. So yeah, if they turn the corner fast enough at full throttle, it'd rotate the wheels and pull them off. Hence the throttle limiting and some of the other things we'll do to make it drive a little more smoothly. That, and when he first put the code together, when you went to turn it, it just flipped the polarity of the one motor, right? So it always turned on a dime, and it always went from going full straight to full right, and that sudden shift was essentially too harsh for the body. So how he limited it, he cut the max. We saw that maximum of the PWM was 255. He cut that down to 175. So we're never at full throttle, at least with the motors that we've got. Again, depending on how advanced your class is, right? If you get 6th graders versus 12th graders, maybe they want to try and make it go to full throttle and they want to find other solutions, different motors, more advanced control scheme, maybe they're more experienced with Arduino systems. There are other ways certainly to do it that would let you go faster. On the other hand, if you want to go faster. So the drawback is we can't accelerate as fast, which is probably not very good. The easiest way to still have this throttle limiting and be able to accelerate as fast is you could take the code and you say when I'm at dead stop, I don't limit the throttle for the next so many seconds, so I can accelerate quickly from 0. But so this is the bot the student that worked with me first built. So, first version of the bot before I made it use shorter wires and get the movement on the side of it.
Can I ask a quick question?
Yeah.
What is the competition like? I mean, we saw a little bit. What is the goal? What are you trying to do in the competition? Are you trying to like break the other one? Just get it to like, what is the goal?
Yes. You're trying to break the other bot.
Okay.
Last bot standing. So basically it's a bracket style double elimination tournament like you see in Little League Baseball or basketball. So your objective is to knock the other bot out or score enough points that you advance and they don't. The point system is things like cornering their bots or I'm drawing a blank on what the point system is. I can show you the document that outlines all that. The arena is that I have that we built here is 8 foot by 8 foot, 2 foot high, steel base with a plywood top and plexiglass enclosure around it for them to watch it. Basically, you put the bot in, you turn it on, you close the glass. Nobody's allowed to open it until after the match is over. Matches are 3 minutes. And the points really come in if nobody is disabled. So if they were to do that, there's also the general rule is there's 20 minutes between matches for a given team. That way they have a chance. If they lost match 1, their second match, they've got 20 minutes to put it back together. A little bit. I also advise our Baja design car team, and so there's a racing competition at the end of that tournament where it's an endurance race. Right, so they bring the car back to the pit. If it broke, they've got to fix it and get it back out there. So spare parts are a good idea on that front. Even if you won, you might need to have some spare parts. So, if it's a classroom activity or after school activity, right? They can do 1 match today, have 2 tomorrow. There's no reason it has to be only 20 minutes. Adjusted to your schedule. So, I found some other bots in this 150 gram weight class, the lower weight class. None of these are mine. These are all things I found on YouTube. So I'll skip through. He's built a couple of different kinds of bots. And this is the one he was trying to design. To a picture of it. So he's got a system that's a lot simpler than what we've done because he's eliminated some of the Arduino system. He's bought a receiver that controls the 2-wheel bot. So that piece is bigger than what we have. The trade-off is, and so what he ended up building was here, these are his electronics. There we go. So he can control the motors directly with this receiver. This piece in behind is his on-off switch and light system. integrated together. So much smaller and lighter than what we've done. He ended up having to make custom wheels because if we wanted to listen to the whole thing, he said essentially he put it together, and it the largest wheels he could buy weren't big enough with the 3D printed chassis he made for it to flip. So the purpose of the bot that he's built is it's essentially got a hammer that it flips to smash the other robot. So he took foam tiles from, set up a workout floor in your basement kind of thing. And use the hole saw to cut out his own tiles. And that's great. That's interesting. But the other problem that he talks through here in the video is he got it together. When you see him with the connectors on the motors, he couldn't find motors that were the same resistance. So we can also talk about some of the electrical principles. He kept getting motors. They've got this little gearing system built into them to make them faster and more powerful and all that kind of stuff. Slower and more powerful. But we will trade speed for power. Well, not exactly. We'll trade speed for torque. Power remains constant. So the motors that we've got also have a gearbox that's just built into the plastic casing. Most of the motors we got, if we didn't have a gearbox, would just go really fast and they wouldn't be able to move the box. They have no torque. But anyway, aside, the resistance kept being different. You buy a bunch of motors together, they come in, their resistance is different. Try another site, resistance different. So his solution was he just kept buying motors until he found two that were the same, so that the bot would drive straight. I would have taken a different approach. We could talk to the class about, well, why doesn't it drive straight? What can we do to change it? The controller that we'll have has essentially fine adjustment for the steering and the throttle. And so what I would do instead is start with that. Can I just fine adjust it because it's not quite right, and adjust the signal to get them to go straight? If I can't do that, then I go look at the code and that algebra we did. Instead of when I go straight, power is the same, both are at 150, I put one motor at 150 and one motor at 149, and I try and recalibrate it that way. There's a little bit more learning and active understanding of what's happening going that way. The other way would be if you did want to solder stuff, add a resistor to make both motors have the same resistance, right? So add another resistor to the series. It's a matter of whether we want to do it through financial power of just buying stuff until it matches, or a physical solution of the resistor, or a coding solution of, let's take what we got and figure out how to make it work. The other obvious solution would be, okay, like when your car is out of balance, just hold the steering wheel a little bit to the left to make it go straight, which is not a great solution. It's not even really a good solution. This one's not too interesting. It just shows you a different type of mechanism, right? We've got anything from having the bot flip a hammer. The interesting part about that first one is it's still only two-wheel control. I still have the same control mechanism. All that I do to flip it is I go fast the opposite direction, and the momentum flips it. So it's the motors themselves that are driving the system that also flip the bot. This one had a third motor. This is, I don't know, just went to the next video, but would be an example of a competition, I suppose. The one I wanted to show was this guy. So this is another ant weight bot. It's only 150 grams. He's built it with those forks on it. So again, it has 3 motors. We need that third button on the transmitter to be active, and we need to take the code and have it send the signal from that third button. Actually, we probably don't even need to send that through the Arduino. We could just wire that third button directly to the motor it controls. And what it would do is cause this to flip. So when he puts it together here, he's got much the same parts that we do. I think this bot is primarily all 3D printed. He's using a lithium battery, which, like I said from the beginning, is probably the easiest way to save weight. Instead of using 9-volt and AA batteries like ours is built with, switching over to a lithium battery, we do that when we need to buy battery chargers. I didn't do that to reduce the startup cost. Right, so that's his bot frame there, and essentially what I was saying, this black servo motor here in the front, that's the one that will control the force and cause it to ideally drive it under another bot and use it to flip it. So you don't have to break the other bot, but if you could flip it, that gets you points, right? You've done damage to it, been aggressive, and if you flip it and you get it to the point where it's standing on its end, or if it's a bot that can only drive when it's bottom, when it's upside down, then that's technically a knockout too. So, but yeah, put it all together here. So we can drive it around. This competition video is very interesting. Nothing actually happens. Just drive around in circles for a while. Yeah. So anybody have any questions?
I had some questions about like support. Like, would we be able to ask you to do like 1 or 2 Zoom meetings for 40 minutes with a class?
That was my intention.
Okay.
Yes. That I or my students, 47 teachers signed up for. So I don't know. My initial intention was, yeah, I'll log in all 4 classes. If all 47 teachers want to do it in their class, I'll log in for some of them, and I'll have a grad student or an undergrad log in for some of them to help, because that's 188 classroom logins, and there's not enough time in the semester.
It's good for the kids to see students though too, and
Right.
like what you can do as a student, like at New Mexico Tech, would be great for the kids to see.
Yeah. Yeah, my intention was that I and or some students would log in to some of your classes. Probably not from my office, probably from downstairs in the lab. We can show them a bot, work along with them, help troubleshoot, help answer questions, whatever you want.
It would be great too to maybe have an option of like a student just giving like a, you know, computer video tour of what does the lab look like, you know?
Yes. Yeah, I can definitely do that too. Having somebody from Sandia come up to class, John or Richard, there's a couple of names on that, would be great too. So, the other thing I got here is Exploration Day at Tech is November 6th. It's the traditional fall open house for the university, but it's also, we're going to set up and have the student bots compete in the tournament like last spring. So wanted to extend the invitation to the classes to either come to it if they're close enough and they're interested, or watch it. We'll broadcast it like this on Zoom. They can watch. That was the last one. It was kind of fun. Obviously, the more bots we have, the more interesting it is to watch over Zoom. I don't know exactly how many I'll have for the fall. I'm hoping some of your classes will want to come in the spring, and so that one will be essentially with giving the teams 20 minutes in between to fix their bot. If I only have 3 to 5 bots, there's 20 minutes of downtime. Oh, all right. I see you guys putting it to your ears. I forgot the microphone's in my laptop, not on my big screen. Sorry about that. So, excuse me. There's 20 minutes of downtime. There's another 3-minute match, and then the next 2 teams had time. So there's 10-minute downtime in the next match. So it not quite as continuous as I want it to be eventually. From what I've looked at competitions like it in places like Texas, it takes a year or 2, and then you're hard pressed to fit everything into a day. So that's my goal. It'll be more interesting and more action packed the longer we go. But yeah, so that's the expo day. The presentation I'll send has this flyer for it, and then there's a website. Like I said, it's set up for mostly the high school students that are interested in coming to Tech. There's no reason others couldn't come as well. There's another link here that has more information on it. So there's a little picture there of the tournament from last April. We've got a drone cage and VR flight simulator system over in the library that'll be set up for tours. Director of Space Corps is going to come give a talk to the students, and the Baja team is going to have the car out for prospective students to drive. We only the second time we've opened it up to non-current students to do something like that, drive the car. Yeah. If there's no other questions, I'm gonna run down to the lab and grab the bots. My late start with the computer not turning on this morning, I didn't go get it before we started. All right. Oh, give me 2 minutes, I'll be right back. Or if you guys want to take a break for 5 minutes, and I can just sit in front of the computer this whole time. That's fine too.
Yeah, sounds good. So back at about 10:29, 10:30.
So is this a normal school day for all of you, or you guys get the day to do training?
I think Mesa asks schools to give them the day off.
Okay.
I think Richard, did you get the day off for these sessions? Yeah, good.
There's no subs,
Yeah, that's, oh yeah, we've been hearing that's part of the issue
so
too.
I'm running back and forth.
Cool. Well, so this is what the bot looks like all put together. So we've got the 2 motors and wheels, the power supply from the breadboard, the motor driver in red, the Arduino is this little Nano here. There's no reason you couldn't use a Mega or an Uno or some other form of Arduino. We just changed the pins around a little bit. The transmitter receiver, and there's a AA battery, and the 9-volt battery would plug in here where I've got the cable going down against the wall at the moment. Yeah, this students ordered the wrong kind of cable for the 9-volt battery. Didn't have a barrel connection. So, but yeah, and then the front of it is a separate piece here. We can just go and attach. So like I said, this is the 3D printed version of it. The home core board version that we used this summer, just the same thing, just hot glue and home core board instead of 3D printing. So, well, I'd say a little faster, but it's a lot faster to put together. The drawback of the 3D printed was they're really, really durable. So the electronics don't get damaged, but it also right, and so the control, right, to power it on and off is literally just this push button on. We've actually got a whole bunch of lights to come on. Off, all of them go off. So all 4 of the pieces of electronics clearly see lost their power. To finish off the bot, we generally put a piece of acrylic over the top, or something else. What I generally do is buy 3M Velcro strips to secure all these electronics in here a little more securely in the specific spot. That way the students can still pull them back out and work with them if they want to do something, but they're in there a little more securely, not bouncing around. But anyway, I'll turn it on here. This is the controller. So the wheel on the side is the steering. The trigger underneath is the throttle. Probably seen something like it before. Oh, and that's interesting. So I just finished telling you it only goes in forward. This one's going in reverse. The students just put this together yesterday for our admissions department to take on college or recruiting visits. And so they haven't put that 9-volt battery in it, so they obviously haven't tested it yet. What's interesting about that is it's quite possible your team puts it together and it does the same thing. It goes in reverse the first time. The way to fix that is if I pull out the motor driver, on one end over here, I've got the wires that go to the right motor. On the other end, I've got the black and the red that go to the left motor. I'll just swap these, the red and the black, on either side. So on the right motor side, swap the red and the black. The left motor side, swap the red and the black, and now it'll go forward. Instead of reverse. I don't think I brought a screwdriver upstairs. Unfortunately. So I can't do that right now. But yeah. And however, put it all back in and drag around on the floor backwards. Looks like they still got a loose wire on the second motor. There we go. They are powerful enough if you full turn one direction, it can generally spin itself out of the corner if it gets stuck, even if they haven't implemented reverse. But yeah. The other thing I brought upstairs, so this is give you a size. Oh, you still give you a size comparison. The 3D printed bots that we build. This is the 3-pound bot. It's not actually much larger. The difference is it's aluminum. Primarily. It has 4 motors instead of 2, but it drives exactly the same. There's no steering system. It's just yeah, it's just power to one side versus the other. Controls it. There's a Scorpion Mini. If I put this up to the camera, you see this big red board here in the back. That one does all the processing instead of the Arduino, right? So there's no. It's a board that's specifically built for controlling a bot that's a 2-wheel system. And then, so because I have 4 instead of 2 wheels, I just wire the right 2 motors in the same port as each other, and the left 2 in the same port as each other. But all the other components it has are the same. It has a battery pack that's a lithium battery instead of the pile of 9-volt batteries that are in this other one. Sorry, not but AA batteries. And then it's got a little receiver that pairs to the remote. The nice part about these is they come with the receiver already paired. You don't have to do any of that. Get my Bluetooth thing to talk to the speaker, with the TV Bluetooth to talk to the speaker Bluetooth and get them to pair, and they have to be close enough to each other. You don't have to do any of that. It's already done. Just plug it in, as long as you remember which one is which. I brought 2 controllers up because they didn't. The students put it together last night. They didn't label which one was which, so brought everything. Yeah. Any other questions?
You said that this is on the ME website?
Yeah, the slideshow isn't yet. The slideshow is in my Google Drive, but it's open access. So let me pull up. And with like, put it in the chat. The slides. That's the link to the slideshow. But yeah, I should show you the website too. So this is the Robot Combat website, which is under the Mechanical Engineering Department. Okay. The YouTube videos I showed you of our bots running are here. The other ones I showed you, there's a link in the slideshow, but I literally just Googled ant weight Battlebots. The tournament information is here. Sign up form. There's construction specs for the different weight classes. If in the future you've got teams that you think want to compete, the two weight classes I picked to implement here at Tech are the 150 grams and then the 3 pounds. Weight 3 pounds and 3 pounds. Just you can't possibly do all of them. The TV show, if you remember it, Battlebots, it actually still exists. It's on the channel, I don't remember. But they use these 250 pound robots that go and smash into each other. That's a lot of money, not something I would do as a school project. Something I would do with disposable income. There's the match rules link. So Spark is it's a governing body for robot combat programs, right? They wrote the weight classes rule book. They wrote this match rules rule book, and they wrote the judging guidelines, which are all here. Pretty much follow them exactly in terms of, there are some stuff we can customize. There's a bit in there about using projectiles on your bot or flamethrowers. I don't really want those on campus. Other than that, there's also a bit in there about if you're allowed to use magnets, because you can use an electromagnet to hold your bot to the ground to give it more force as it drives a hammer or something into something. We do have a metal steel floor, so that should be possible. But we're really getting ahead of ourselves with that. Let's see. The workshop, like I said, the document is linked in the thing I sent you. There's also another link to it here. You guys already have my email, so you really need to fill out an inquiry form to have me do stuff with your class. Most of the students in the program here at Tech that have built them or that work with me on helping development are in this Discord server. That's got a link here at the top. I'm happy to provide it to your class if you want the kids to be able to ask questions later. If you've got 6th graders and you don't really want them on Discord, don't give it to them. I leave that totally up to you. The Discord server is something I learned to use during the pandemic for our freshmen to help them develop a sense of community when they couldn't be on campus. They've never been on campus. You know, they've never met anybody. So, yeah, that's what that is. If you don't know what it is, it's essentially an online forum. There's forum rules and things. It's supposed to be kept at an appropriate level or general audience. And students and I should be in there to watch it. That said, it's an online forum, right? Somebody posts something. I'm not 24/7 watching it. So that's why I say decide if you want to share it with your class or not. I don't know exactly what's appropriate at the middle school, high school. Yeah. And that's just a little article about the first set of matches last April.
Who do we tell if we do want to participate?